Okay, let's pick up where we left off in Chapter 5, which is Section 5114. I've already gone to that page, and we're going to talk about the Ethernet frame fields again. We talked about this a little bit last lecture. But here they show you the six, what they call Ethernet frame fields. And like I told you, I really feel the preamble at the beginning should be divided into the preamble and the start frame delimiter. So, if I show you this figure on your first exam, which is highly likely, or at least ask information from it, the preamble is going to be the preamble and the start frame delimiter, which they even talk about down here. So you have 7 bytes. Again, the preamble is just a series of 0, 1, 0, 1, 0, 1, etc. for the 7 bytes. And then that allows the NIC card to lock on to the bit time and figure out where the transitions are occurring and make sure it has and is reading those correctly. And then finally, it'll lock on and it'll sit there and watch the 0, 1, 0, 1, 0, 1. When we go into the start frame delimiter, it'll be 0, 1, 0, 1, 0, 1, 1, 1. And when it sees that 1, 1, it knows that it is now to the point right here, and the next thing it sees is the destination MAC address. And if I was in class at this point, I would say, and a MAC address has how many bits? And of course the answer is 48. So if we click here under the destination, it says it is a 6-byte field. 6 times 8 is 48, so there's 48 bits there. And it is going to have a layer 2 or MAC address, and it is going to be the destination that we are sending this packet to on the local area network. Again, MAC addresses are only valid and used on the local area network at layer 2. There is a reason that the destination comes before the source. We'll talk about that when we talk a little bit more in detail about how routers work. So the source MAC address is going to be the NIC or interface 48-bit address of the device that is sending this frame. The type /length tells either the length of the packet if this is less than 600 in hexadecimal. If it's greater than 600 in hexadecimal, it is going to be a type. So for example, if that value is set to 800, it's going to say, what I have encapsulated inside here is a IP packet. If it's 86DD, then it's IP version 6. If it's 806 hex, then it's going to be an ARP request. And notice this is a common way to represent something in hexadecimal is to have a 0 and an X followed by some hex digits. So I don't know if we have seen that before. Next comes the actual data. I'm not sure if we talked about this before or not. I believe we did. The data field has to be at least 46 bytes long, and it can be up to 1500 bytes. If you've ever done any networking, you may see the 1500 number referred to as an MTU, or maximum transfer unit. So this is the data that is going to be sent in the frame. It's probably something that's encapsulated from layer 3, quite often TCP packets. And then we have the frame check sequence. And this is 4 bytes. It is used to detect errors in the frame. It uses something called a cyclic redundancy check to do that. But basically, you perform, the device sending this packet will perform some type of arithmetic operation. For example, maybe you take pairs of bytes, add them together, keep adding them together, keeping a running sum. If that running sum overflows the 32 bits that the frame check sequence is, then it will throw that leading bit away and just kind of roll over and start again at 0. and whatever value that has that it calculates for the packet, it encodes that in the frame and then sends it. When the frame makes it to the other end, it performs the exact same calculation, and you can't really use the preamble to perform the calculation because part of this is going to be lost if the NIC card hasn't locked on yet. So we start at the destination MAC address, perform whatever arithmetic operation till we get to the end of the data. Then we put the result in the frame check sequence. When this packet is received as destination, same thing occurs. It may lose part of the preamble, but once it knows where the starter frame is, right here, it will start performing the same mathematical calculation. And when it gets to the end of the data, it'll come up with a numeric value. It will compare that numeric value to the numeric value that was inserted in the frame check sequence. And if they match, then the frame is intact. If they do not match, then there's some type of problem, and the frame will not be considered valid. Here's an activity based on a little bit on last lecture, or primarily on last lecture it looks like, where you can go through and you have some characteristics, and then you would check whether that's referring to the MAC layer or the logical link control layer, the LLC. So you can do that activity on your own. Here's another activity. Can you piece together the information? Again, I want you to note that it has the 7 fields that I like. So this is how it's going to be destined. So the preamble would come first, and then start frame delimiter, etc. So you can do that to make sure that you have the field names and what they're used for in the correct order. And then here's another way that you can go through. Again, this is 7 fields, so I'm always going to ask you on a test. The other thing too that's important to know is how many bytes are in each of these. Some of them are easy. Frame checksum's 4. The MAC addresses are of course 6. But you probably need to start getting a feel for how long each of these fields are as well. Okay, recently you had a lab to install Wireshark, and then one to go through and at least start using Wireshark. This one is called Using Wireshark to Examine Ethernet Frames. So we're going to be doing layer 2 stuff. As I mentioned before, Wireshark is really good at breaking the packets apart and kind of giving you the information in quote English, so that's easy. So watch for this lab 5117 to appear, but it's using Wireshark again to look at layer 2 stuff. Okay, MAC addresses and hexadecimal. I've of course taught you about number conversion. One of the first things we did was binary. The next thing we did was hexadecimal, and then the third thing we talked about was octal base 8. And I showed you some tricks with base 8. This is kind of related to the trick I showed you. So if we have half a byte, which is kind of corny, but it's called a nibble. There are 4 bits, so there's 2 nibbles to a byte. Each of these nibbles in binary can go from 000 to 1111, which matches up perfectly with hexadecimal, 0 through F, which of course is 15. So what happens is oftentimes, and this is partially why hexadecimal is so popular in computing, is because you can represent a byte as exactly 2 hexadecimal digits. So that's what they're showing you here in this table. Now if we go to the second figure in this section, they're showing you just that. Here's a byte. So the first nibble is 0, second nibble 0, so it's represented as 0, 0. All the way down to a bite, which every bit is set to 1, which is represented as F, F. So that is 256 values that goes from 0 to 255. They've obviously started jumping around and skipping big sections because they didn't want to show you a graphic that had 256 lines in it. That would be a little bit difficult. Like I said, I've taught you the trick. This is kind of based on that trick, going between binary and base 16. This is talking about the MAC address. The MAC address is 48 bits. The way they divide this is they divide it right in the middle, 24 bits and 24 bits. The left half of this, the first 24 bits, is referred to as the organizationally unique identifier. So basically, from those 24 bits, you can tell who manufactured a NIC card. So here they're saying if these 6 hex digits are 00602F, that means Cisco made the NIC card. And then the remaining 24 bits are set by the vendor, and they are presumed to be unique amongst themselves. So Cisco should not produce 2 NIC cards that have the exact same MAC addresses. Down here they're saying that could happen if there was a mistake during manufacturing. If those NIC cards with identical MAC addresses went to 2 different places or ended up on 2 different LANs, we would be okay. But if somehow they manufactured 2, they went to the same place, they ended up on the same network, then we're going to have a problem. It would be like 2 people in Lexington having the same cell phone number. That's not the way it's designed to work. One thing, I think they've mentioned this before, and they may mention it on this page, but sometimes the statement will be made that the MAC address is encoded by the vendor and can never be changed. There are some reasons to want to change a NIC address and or a NIC's MAC address, and some NICs allow you to do this. An example, there's really one example that kind of tells you what we want to do this for. So let's say you have a server, and you have that server for 4 or 5 years, and during those 4 or 5 years you put a DHCP entry in for that machine. You have software that is licensed based on the MAC address, which is very common, and you license all this software and everything, and now all of a sudden you get a new server. Well, you don't want to have to go through and contact every vendor and get new license codes and possibly miss something. You would just like it to work like it did before on your older machine. Sometimes what happens is when you bring a machine up, for example, Sun machines will at the beginning say, do you want to change the MAC address or not? And you have that one time to do it. So what you would do is you would say, yes, I would like to change the MAC address. I'm going to change the MAC address to match my old server. And then that way when it comes up, all the software is going to work, all the licensing will work, etc. There are some others. I don't know what Apple's current policy is, but used to, they would allow you to change the MAC address of a laptop. I believe it was 5 times. Some people will change the MAC address to hack or so they can't be traced, but the example I gave you is one of the legitimate reasons to want to change that. Okay, so what I'm going to do is I am going to play this animation. They probably should have this on the graphic, but basically host 1 here is going to have the MAC address of AA, 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 and then it's going to talk to host 3, which has the MAC address of all Cs. So CC, CC, etc. So when I play this, what's going to happen is it's going to want to send information to host 3. So it will encode its address in the source, the destination as all Cs. Since this, it will go through and all the hosts will see it. They will check the destination address and say, is this me? And in the case of H2 and H4, no, it's not destined for me, so I'm going to ignore it. But in the case of H3, who has the MAC address of all Cs, since that is the destination address, H3 will say, okay, this frame is intended for me, and it will pass it up the protocol stack and process that. This page is showing you some of the ways that MAC addresses are represented. Here is an ipconfig/all on a Windows machine, a command that you will probably use many times over the course of the semester. It gives you information about all the adapters. They're only showing you one, or this machine only has one. And the MAC address is sometimes called the physical address or the hardware address. So in Windows, they call it the physical address. And here are the 6 hexadecimal represented bytes with minus signs between them. So the minus sign is one way to show a MAC address. Another way that some people show the MAC addresses is they actually do 4 bytes or 4 hex digits, period, 4 hex digits, period, 4 hex digits. So you end up with 12 digits the same way. The most common way that I've seen, and the way that I prefer, is to actually put colons where all the minuses are. So you would still have 6 pairs of hex digits, but they would be separated by a colon. So they're basically showing you with dashes, with colons, or with a period. And whatever organization you work for may have a preferred method. If you're sending network requests, they may say you need to do it with colons separated between. Okay, so we talked about unicast and broadcast and multicast before, but to refresh your memory, unicast, as uni1 implies, is a one-for-one message. So in this case, the source MAC is the MAC address of host 1. So host 1 is there. Now the destination MAC is the server that we're going to. And the IP packet will have the source IP and the destination IP encoded in it, and then it would have the data that it was wanting to send. So this is what the packet will look like. So what happens is host 1 will send it, and will go straight to the server. We haven't talked about this a lot, but switches will learn over time what devices, or more accurately, what MAC addresses are on each of the ports. So if it knows where the server is, it will only send it out that one port like it did here. I don't think we've talked about it yet, but if it didn't know where that MAC address exists, then it would send it out every port other than the port it came in, which is kind of what we saw in the last graphic, and that is called flooding. Now then, one thing they mention here, they say it's discussed later in the chapter, but since they mention it, I'll go ahead and mention it, which is ARP, Address Resolution Protocol. Layer 3 wants to communicate using IP addresses. So what would really happen is we would have our IP packet here, and when we wanted to send it, our source host would send out an ARP request and basically say, I need to communicate with the machine that has the IP address 192 192.168.1.200. And that machine will reply back and basically say, hey, that's me, here's my MAC address. It will then stuff that MAC address into the frame, and then it is able to send it. So that's how IP addresses get mapped into MAC addresses. I don't know if they talk about it anytime soon, but the reverse process, hey, I have a MAC address and I want to know what IP address is at that MAC, it would use reverse ARP, or RARP, stands for Reverse Address Resolution Protocol. So we're going backwards of the way that ARP works. Okay, 5126 is talking about a broadcast MAC address. Again, let's go ahead and look at the IP packet that's here. The source packet is 192.168.1.5. This is a Class C address. This is the one that we've looked at most of the time. So the dividing point between the network portion and the host portion is right here. The way we designate an IP broadcast address is by setting all the host bits to 1. So 192.168.1.255 cannot be used for a host address because it is the IP broadcast address for the 192.168.1.0 network. And 0 can't be used because that is the network number. So what happens is, if that's the case, the destination MAC is going to be all bits set to 1, which is all these Fs that we see here. So what happens is the switch knows it's a broadcast, so the frame comes into the switch and it sends it to all the hosts on the network, which is the way we defined what broadcast meant. Okay, multicast is a little more strange. It's a one-to-many. So what happens if we talk about it from layer 3, IP? IP addresses that start with 224 are multicast addresses. And then you encoded in that have a multicast group. So what happens is the source MAC comes from host 1. These machines, the 3 up here at the top, this server and these 2 desktops, are in the multicast group. So they will know. So the multicast group is actually 224.0.0.0 all the way up to 239.255, 255, 255. At layer 2, multicast MAC addresses are 010050, which you can see over here in the destination MAC, and the rest of the MAC address is the multicast IP address, the 23 bits. Or the bits for that. So 200, for example, the end of the IP, translates to 11001000. So that's C8. So again, just like in decimal, we can pad in front with zeros. So that's how the multicast group is encoded into the destination MAC. Okay, 5128 is something that if this was an in-person class we would do in lab, but this will probably be one of the first labs that you do on the NetLab. I have a video or a handout and possibly a video coming up on the NetLab that I've been trying to work out. We're in the process of trying to upgrade the NetLab, but we're probably going to have to start the semester with the old NetLab, which has some issues, primarily Java related. The new NetLab uses all HTML5, so fortunately those issues will go away. But more on that later. So right now, just read through the 5 pages of 5128. The reason I tell you to read through that is occasionally, they've been pretty good lately, but occasionally in the past, they would ask you a question on a chapter exam that the only place that it was mentioned was in a lab. So even though we're going to do that later, go ahead and read over that prior to taking your Chapter 5 online exam. Okay, so we're going to go back and talk about switches. They don't talk about it so much in the curriculum or the way they used to, making it quite so obvious. But at layer 1, we have things like the media, the NIC card, and that type of thing, possibly hubs. Switches are a layer 2 thing. That means they operate and do things with Ethernet frames, and the addresses within there are MAC addresses because we are at layer 2. So here we have a 4-port switch, and we have a computer connected to each of these. Now, it's not saying this is an Apple Macintosh, for example, but what it's saying is to make things easy, we're going to shorten the MAC addresses down to, just 4 characters. Really just 1, A, B, C, and D. If that bothers you, just pretend there are, zeros padded out to make this 48 bits long. But in a switch, we have something called a MAC address table. And for each there will be an entry for, or possibly even multiple entries for each port. Right now we'll assume there's only one device connected to one port. If that was true, then we would have 4 ports listed. And as these machines sent something to the switch, it would populate the MAC address into this MAC address table. That way the switch knows where MAC addresses are. So if something comes in destined for one of the MAC addresses, it'll know what port to send it out. And again, if for some reason it doesn't know where that MAC address is because possibly the machine has not talked to the switch or through the switch yet, then it will flood. And flooding is sending a frame out every port other than the port it came in on. So 5212 talks about this learning process. So here we assume that computer A sends something through the switch. What the switch will do is it'll say, hey, on port 1, I have a device that has this MAC address. So it gets that from the source address. And basically over here it's saying I don't have the source MAC, so let me add it to my table. Since it does not know where D is, it has to flood it all the way out. So these 3 machines, B, C, and D, all see the frame. B and C would both say, not for me, and ignore it. D would say, hey, it's for me, I'll process it. The switch still doesn't know where D is. D would actually have to talk back to A or another host for its entry to make it into the MAC address table. So flooding, I have a note here in my notes, says to mention that flooding is also done for broadcast, which we talked about, and multicast frames. So it will send it all out and let the host decide if they're in that multicast group or not. Okay, this is showing us that we're going to assume that D talks back. It is on port 4. D's MAC address is 000D, so it puts that into its MAC address table. So this is continuing on from what we had before. If we go to figure 2, it was sending a packet from D to A. The switch does know where A is, so it will simply send it out A to PCA. Sorry, you'll send it out port 1 to PCA. Now, if A is going to talk back to D, same thing happens. It goes in port 1. The switch says, hey, I know where D is. It's on port 4, so let me send it out. So once the switch MAC address table is fully populated, this cuts down on bandwidth being wasted sending to machines and possibly computing power being wasted for examining packets that are not even destined for those. One thing they do mention over here is if a machine has not talked through the switch for a 5-minute period, it will remove that entry. If that machine talks at some point after that 5 minutes, it'll simply put it back in its MAC address table. .5214 is basically a video version of what we talked about. It's a little more involved. It has two 4-port switches, switch 1 and switch 2. And then it does have a router that has a connection to the switch as well as to the internet. So it is about 3 minutes and 9 seconds long. So I highly recommend you watch it outside of class. It reinforces what we just talked about with a slightly larger example. Okay, this video is also right at 3 minutes. I'm not going to talk about it. I'm not going to play it, but I'm going to talk about one aspect, which is the default gateway. I think we've talked about this before, but it's a very important concept. I'll back up one step. One of the questions that I can guarantee you is going to be on your exam. Always guarantee it. I've actually already started working on your exam. Is what are the 3 pieces of information that need to be properly configured on a device for it to communicate on the internet, capital I? And the answer is it has to have an IP address. It has to have a subnet mask. Again, the purpose of subnet mask is to divide an IP address somewhere in the middle. What's on the left is referred to as the network portion of the address. What's on the right of that division point is referred to the host identifier or the host address or a particular host on that network. Different ways to say the same thing. If the destination IP is not on the same network, then it will send it to its default gateway, which is going to be a router that exists on the edge of whatever networking cloud you have. For example, if you're at home, you may possibly have multiple devices inside your home cloud, and the edge of that home cloud will be your multifunction device, which is a router that'll most likely be a device that you got from your ISP. So the default gateway, gateway of last resort, default router are all ways to refer to this. So what this is showing you is you're going to be communicating with a device, I suspect, that is not on the same network as all these other devices. So it will need to look up and communicate with the default gateway, which is going to be this router, so that it can take the IP packet from your local network and send it out over the internet, capital I in this case. This is one of my all-time absolute favorite activities in the whole curriculum. So what happens is it will show you a setup over here. And the really nice thing about this is you can go new problem and you will see things changing, like where packets are coming from, what the source and destination MACs are, and what portion of the MAC address table in the switch is populated. And notice that port 9 has a hub and it actually has 2 computers connected. So there would be potentially 2 entries for port 9 because it can see 2 MAC addresses. The other thing you need to know about this is when a frame is flooded, It only goes out ports that have devices connected to them. Let me do a new problem. So the frame is coming out of A. It is going to C. We do not know where C is. So what it'll do is it'll send it out port 3, 5, 7, and 9 because it does not know where the destination is. A is not populated, so that will be added to the MAC address table. It is not a broadcast because the destination MAC is not all ones. It is a unicast frame and will be sent to specific ports. Well, that's false because we don't know where it is. So the frame is unicast and will be flooded to all ports, but it will be dropped at the switch. No, that's not true. So there we go. I think the problem in the first one was because we were sending on the same network, so that was a little confusing. But if you go through, this little activity teaches you quite a bit about dealing with switches and MAC address tables. This is a lab where we go through and actually look at the MAC address tables that are being stored in switches. Again, we would do this in class if this was an in-person class, but since it's not, look for an activity related to that. Now then, I told you we were going to talk about why the destination MAC comes before the source. That just seems kind of strange. And it has to do with the way packets are switched. A lot of switches will read the whole packet. They will calculate the frame check sequence while they do that. They will verify that the frame's intact, and then they will figure out what port or what flooding needs to be done to get that packet to its destination. However, some switches use what are called cut-through. And when they're cut through, they look at the preamble, they find the start frame delimiter, and then they look at the MAC address, and that's really all they need to do to make the decision where to send the packet. So that packet that's partially come through the switch will start being transmitted out the appropriate port or ports, and as the rest of the frame is read, it will be sent out the same set of ports. So that just makes the switching quite a bit faster. So this is store and forward. So in store and forward, we're going to have a little memory on the switch that will buffer up or store that frame. It will check the CRC. In this case, they match. So then it will examine where it needs to go from its switching table, and it will send it out the correct port, which in this case is the PC on the right. The next one is going to show you cut-through switching. So you'll notice that it'll start forwarding the packet after it's read the MAC address. So the destination is sending it back. It looks at the switching table and starts sending it out the source. Now, I think a little better representation would be if they got a portion of the frame in the switch, then they showed you it examining the MAC address, and then start sending the packet out of the left of the switch as it was coming in the right switch. So it didn't show you the cut-through switching very well, in my opinion. A switch and routers are very specialized computers. They will have memory buffers that are used for storing information. For example, the MAC address table will be in memory. You may have memory that is associated with each port that may be used for buffering up or queuing information while decisions are made as to where that frame needs to go. Or you might have a bigger set of shared memory that is shared amongst all of the ports on the switch. But the important thing to kind of take away from this is you have to have memory to buffer these things up. Even with cut through, you need some memory to store things up before you can look at the destination MAC address. This is an activity related to frame forwarding, things that we've been talking about. So you can look over this yourself. This is a description. Does this best match up with store and forward and or the cut through process that we talked about? This activity also has a figure 2 that goes through and talks about different things on here. So, what cabling is used, what's the data frames and that type of thing related, and what will the switch do to the packet. So you can go through and do that and check that on your own. Okay, this is the point I would like to get to.